We are now ready to review combining these ideas into a fundamental concept for statistical inference. Right? This is the central limit theorem. The central limit theorem combines what we know about the standard normal distribution model, the normal coverage rule, and sampling theory. The central limit theorem states that if random samples of size n are drawn repeatedly from any population, in which that population is a mean mu and a variance sigma squared, then when the sample size is relatively large, approximately greater than 30 for most distributions, the distribution of these sample means will be approximately normal. This is how we can write the central limit theorem. The distribution of sample means, the sample means are distributed normally, centered on mu, with a spread of sigma squared divided by lowercase n, where lowercase n, that's the sample size. Right? The square root of sigma squared divided by lowercase n, the standard deviation of that distribution of sample means, we call the standard error of the sample mean. It gives us an idea of how far off we expect any particular sample mean to be from the population mean. This is a very cool theorem, right? Because it says that, it not only says, it talks about the center and spread of the distribution, but it talks about the shape of the distribution. It says the distribution of sample means is symmetric and mound-shaped. It's approximately normal. So the central limit theorem says, okay, we know roughly the center, we know the spread, and we know the shape. The shape is roughly normal. Now this is very cool because it tells us that even though we don't repeatedly randomly take samples of a particular size from a population and create this distribution of sample means, even though we don't do that in practice, we can know the shape of this distribution, and we can use this distribution of sample means to make inferences about a population, even though we only have knowledge about a particular sample and the process by which we gathered that sample from the population. That is random sampling. So this is one way to view what we call the sampling distribution. The sampling distribution of sample means is simply this hypothetical, this abstract distribution of sample means. Now, repeatedly drawn from the same population. Now, what this tells us is that no matter what the underlying distribution of the population, that distribution of sample means will be approximately normal. And the spread, right, of that sampling distribution will get smaller and smaller and smaller as the sample size increases. To put another way, the sample means are going to differ not as much if you have sample means that are based on larger samples, which makes sense. You know, if you have a population of 100,000 people and you calculate a bunch of samples, sample means rather, based on samples of size 10 versus size 5,000, right, you're going to expect those sample means based on size 10 to differ a lot more from each other, and that's going to appear as a larger spread in the sampling distribution. So what's cool about the central limit theorem is that it tells us about the shape of the distribution. It also tells us what we expect a larger sample size to do in terms of the shape of that distribution. The larger the sample size, the larger that denominator, that spread of that distribution, the standard error of that sample mean is going to get smaller. From this, we can create interval estimates. A point estimate for some population parameter is simply that sample analog. So for example, the sample average for your particular sample, that's the best guess. That's the point estimate for a population mean. We also can construct interval estimates based on what we know about the central limit theorem. So we can think of the mean of a random sample as a point estimate, but using the concept of the standard error of the sample mean, we can create a confidence interval. An approximate 95% confidence interval for the sample mean is simply that point estimate, that sample mean, plus or minus 2 times the standard error of the sample mean, or which we call the standard error for short. Right? This is a visualization. Right? This is a way of thinking about all these confidence intervals. We can think of a bunch of confidence intervals, but that population mean is fixed. Okay? We have a sampling distribution that's given at the top of this graph. That is the sampling distribution. It can be modeled using the normal distribution model. Right? It has a certain, the center, that center is mu, that population mean, and the spread is that standard error of the sample mean, right? It's sigma divided by the square root of n. Well, for each particular sample mean, we can think of putting an upper and lower bound, a range of possible values. And so what we can say is we can talk about confidence of our intervals. So in this case, when we talk about confidence of intervals, so here we have 100 confidence intervals based on 100 different random samples of the same sample size from that population, we can say, well, we're 95% confident. We expect 95% of these intervals to contain the true population mean. See that population mean mu? Okay, it's going to go through 95% of those intervals. Right? You don't know where in the interval it's going to be located, but you'd expect 95% of those intervals to contain the true population mean. That's because we know about the shape of the sampling distribution. Right? We have a pretty good idea of what it looks like. It's going to be approximately normal, especially when the sample size is pretty large. To calculate confidence intervals of any size, right, we don't use 2, we can use what we call ZStar. Okay? It's x plus or minus ZStar times the standard error, which is sigma divided by the square root of n. For ZStar equals 1.96, that's roughly a 95% confidence interval. From this, we know that 95% of the sample means are within plus or minus 1.96 standard deviations of the population mean on the sampling distribution. Sometimes Z-star, sometimes it's written as Z alpha divided by 2. So we might say that X bar plus or minus Z alpha divided by 2 times the standard error is our interval estimate. That's our confidence interval, where the size of the interval is governed by alpha, the confidence of our interval. All right, so confidence interval percentage is given by 1 minus alpha times 100. So an alpha of 0.05, that implies a 95% confidence interval. And then the Z star is based on Z alpha divided by 2. So it'd be plus 1.96 and minus 1.96 on the standard normal distribution. In this notation, alpha is the probability of a type 1 error or a false alarm. That's the probability of rejecting the null when it is in fact true. There is a trade-off when we construct these confidence intervals for a given sample size. A higher confidence level is going to give us more certainty that the true population parameter is somewhere in our interval estimate. It's somewhere in our confidence interval. Right? But the problem with this higher level of certainty, right, with these wider intervals, is that they may be too wide to be of substantive interest. So think of it this way. I know 100% with 100% certainty that everybody listening to this lecture is within 98 million miles of where I'm giving this lecture. Everybody lives within 98 million miles. Well, that's a really wide interval. That's not, I'm 100% confident, but it's not very meaningful. It'd be more meaningful to say I'm 95% confident that most people live within 2,000 miles of where I'm giving this lecture. So the idea is that there's this trade-off, right? The formula for the confidence interval of a mean, is a function of our standard error. All right, it's a sample size function. It's also a function of the population variance or population standard deviation equivalently, and it's also a function of Z alpha divided by 2. So we don't have control over the population spread. We do have control over the sample size. We have control over setting alpha, right, which affects our level of confidence. So we might say, well, for a given sample size, what happens when we change the level of alpha? What happens when we change the level of confidence? Well, here's a visualization of constructing confidence intervals with various levels of confidence, with various levels of alpha. And you can see that with 99% confidence, okay, the intervals are wider. Okay? With a 50% confidence interval, about half on average, we'd expect about half the intervals not contain the true population parameter. So there's a trade-off here. Okay? You can be higher level of confidence. Those intervals are going to contain the true population parameter, but the intervals might be too wide. With a lower level of confidence, right, you're going to have narrower intervals, but those intervals are less likely to contain the true population parameter. Another issue is to think about the type 1 and type 2 errors involved. We're going to focus more on what's called the alpha error, or the type 1 error. This is the probability of rejecting the null when in fact it is true. The beta error, sometimes called a type 2 error, is failing to reject the null when in fact it is false. So when we set alpha, right, in essence we're talking about how comfortable we are with committing a type 1 error of rejecting the null when in fact it is true. Another issue has to deal with this idea of using the normal distribution model for the sampling distribution for sample means. Now, if you look at the central limit theorem, it really only works best if the sample size is relatively large, say roughly above 30. Well, the t distribution model, it's a variant on the normal distribution model, except what it does is that the shape alters slightly depending on the effective degrees of freedom, on the sample size. Right? The basic idea is that with a smaller sample size used to calculate, say, a sample mean, right, the graph is going to, the probability model rather, is going to penalize. Okay? It's going to take into account the fact that sample means based on smaller sample sizes, we expect more variability in the sampling distribution. And so the t distribution changes right? With smaller sample sizes leading to a distribution with fatter tails, reflecting greater uncertainty. And then as the sample size gets larger, the t-distribution looks more and more like the normal distribution model, such that if you really have a sample size above 50 or 100, the t-distribution model looks really close to the normal distribution model. It's imperceptible, at least visually, from my perspective. So at this point, we've really covered the basics of inference. These are the foundational parts of inference. Okay? We have the central limit theorem, which is based on the standard normal distribution model and what we know about sampling variability. So when you have a random sample from a population, we can characterize that distribution of sample means because we know how the sample was collected. It was collected through randomization from a population. We also can model the sampling distribution using the t-distribution, which is a more general form of the normal distribution model. It's appropriate for both small samples and large samples, where small is roughly below a sample size of 30. And with that, we're ready to talk in more depth about inferential statistics for means and proportions.